So a tangent is what we're talking about today. A tangent is a line, and it intersects a circle at exactly 1 point. Exactly 1 point. Not less, not more. Exactly 1 point. The point where the line intersects the circle is called the point of tangency. So in this case, you see right there, the line just basically brushes up against the circle, touches it at 1 point, and moves on. All right, so tangents are pretty important in the world of circles. One of the important things we're going to talk about is if you have a line tangent to a circle and, well, actually, I'll say it the other way. A line is tangent to a circle if it is perpendicular to the radius at the point of tangency. So here's the point of tangency. Okay? If you have the radius here, and if you have a line that's perpendicular to the radius at the point of tangency, then that's a tangent. And vice versa. If you have a tangent, then the radius is perpendicular at the point of tangency. So it goes both ways. So let's take a look at this example. You're told that BC is tangent to circle A at point C, and you need to find the value of x. So if BC is a tangent line, what do I know about segment AC? What is that? Right, but that's the what? That's the what of the circle? That's the radius of the circle. So what we have there is that the radius is here and the tangent is here. Well, if this is a tangent and that's the radius drawn to the point of tangency, then we know that they're perpendicular. So you use the Pythagorean theorem. And it's just going to be x squared plus 14 squared is equal to 17 squared. And we all know by now that 14 squared is 196. That's equal to 289. X squared is 93. So x is the square root of 93. All right? So just remember, if the radius meets the tangent at the point of tangency, then they're perpendicular. Here's another one. QS is tangent at point Q. Find the value of x. So again, here is a tangent, and QR meets the tangent at the point of tangency. That means this is a 90-degree angle. All right? Now, we need to find the value of x. Okay, so here's a triangle, right? How big is this side of the triangle? X plus 2, right? Not 2x, but 2 plus x. All right? So that's the hypotenuse of the triangle. How big are the legs of the triangle? 4 and what? And x, right? Exactly. This is 4. This is a radius. And we're given here that the radius is x, so that's also x. All right? So that takes advantage of the property of radii, right? Okay, so now I have that x squared plus 4 squared is equal to x plus 2 squared. This is x squared plus 16 equal to what? X squared plus 4x plus 4. The x squares just go away because you can subtract an x squared from both sides and they go away. That just means that 12 is equal to 4x. So x is equal to 3. All right? So then how big does that make the sides of the triangle, by the way? 3 and 4 and 5. 3, 4, 5, right? Which we know is a right triangle. Yeah.
Did you get the 4?
Oops, what happened here?
Oh, never mind, I know.
You see, okay. All right. Yeah, that 4x there. Okay, so now this is the opposite question. It says determine whether PQ is tangent to R, right? If PQ was tangent to circle R, then what would happen automatically by that theorem? That would be a right triangle, exactly. So if PQ was a tangent, right, then this would be a right triangle. So now we have to see, is PQR, is triangle PQR a right triangle? Well, let's see. How do we test if something is a right triangle? Huh? Pythagorean theorem, right? So how big are the legs of this triangle, supposedly? 4 and 5. So 4 squared plus 5 squared. Is this equal to, how big is this side? 8. Right? Because if this radius is 4, then that radius is also 4. So here we have 16 plus 25. Is this equal to 64? 41 is not equal to 64. That's how you show the work. So this is not a tangent. If this was not an honors class and you forgot the question marks, I don't think I would be, I would care as much as, in an honors class. It's all about the elegant, sophisticated notation. All right, so here's another theorem that I absolutely love. You have a circle, and you have a point somewhere outside of the circle. All right? Now, suppose you draw a tangent from the point to the circle, and then you draw another tangent from the point to the circle. Well, guess what? Those two tangent lines are equal to each other. Okay? Yeah. Right, so if two segments from the same exterior point are tangent to the circle, then they are congruent, okay? So I always say, suppose there was a huge meteor falling on the earth, and, okay, that's it, it's there. NASA somehow, they had their antenna off, right? The satellites off, and they didn't know, and now it's here. Nobody can save us except for who? Spider-Man. So Spider-Man comes and he lets out, his net from both hands to catch this thing. Well, guess what? He would let out equal amounts of net from each hand in order to catch the meteor in outer space. Wow. Yeah. All right. I know. So AB is going to be congruent to BC. So basically you've got two tangents. They must be tangents and they must be coming from the same point. Okay? Now, how would you prove theorem 10.11? They're back. They're back, but we're not going to do it formally, right? But how would we prove it? So suppose you're given that BD and CD are tangent to circle A. You want to prove that BD is congruent to CD. So how would you prove this? How would you? Based on what we know. I know you guys have been missing proofs, so I figured, you know what, I'll throw this in there, to make it a little interesting.
Okay, it's probably not going to be easy.
Uh-huh.
But if we draw...
Look, so we're going to draw, okay, so if these are tangents, the only thing we know is that tangents are perpendicular to the radius at the point of tangency. So why don't I just draw radii to the points of tangency? So one right there, and that's going to be perpendicular because, the theorem says so, and we now believe it to be true. And one right there. Yes. And now we're going to make two triangles. What additional segment do I need to draw to make two triangles here? AD. Okay? Now, these are radii, so they're congruent to each other. Yes? So AB is congruent to AC because they're radii. Okay? And this is another way we can prove something, right? It's almost a two-column proof, but we're going to do it this way. Next, this line AD is congruent to AD, right? Reflexive property. Okay. Now, what else? The angles are congruent. Angle ABD is congruent to angle ACD. Now, if we're doing a formal proof, there would be another step, right? There would be a step where we establish that those are right triangles because the theorem says that they're going to be right triangles. I mean, right angles, right? So here, right angles are congruent. Okay. Now, can we prove that the two triangles are congruent based on what we have?
Yeah.
By what theorem?
No, you can't lose SSI or
And if we had a case like that, and if it was a right triangle, what other option did we have?
Right triangles, no. The other
It started with an H.
Hypotenuse
H.
HL. So triangle ABD is congruent to triangle CAD HL. And now, what do we know now? CPCTC BD is congruent to CD CPCTC. All right? Just to, make sure that you're not missing it too much.
It's going to be on the test.
It's fair game. Anything we do in class is fair game for the test. Yeah.
But how
I wouldn't dare deprive you of that ecstasy, right? I mean, no way. All right. What do we have here? What is AB? It's a tangent. What is AC? Also a tangent. Where do they both come from?
circle
The same. Where do these tangents originate?
the same exterior?
A, right? And if they originate at the same exterior point, then what do we know about them? They're congruent. Now, what do I know about AD and AC?
They also have the same.
They're also congruent. So by the transitive property, everything is congruent to everything, right?
Yeah.
So now can I find X?
Yeah.
So go ahead and find X. All right, so X is 4. And, okay, so go ahead and do the next one. What do we know about the next one? Right. And I'll pause for the people at home here. And we're back. X is 11, Y equals 1, right? Okay, last one. Triangle JKL is circumscribed about circle R. Find the value of X and the perimeter of triangle JKL. Okay. So for this, we need to find X first, then we need to find the perimeter of this. Any ideas? Yeah.
All the sides are equal to each other.
Are they? So look at this. Look at OL. And look at LN. What are those? They're both tangents that originate from the same point, which means they are congruent to each other. So 4x minus 9 is equal to x plus 3, which means x is equal to how much? X is equal to 4. Okay? So if x is equal to 4, how big is this side? What's 4x minus 9? This is 7, and this is 7. So what do I know then? So this is 7, right? All right, so go ahead and find the, well, this goes here. Yeah? Right, this is a radius, and that's a radius. They're the same length. And the distance from here to here is the same as OL, sorry. So it's 7. And this is LN, right? So that's 7. So how are we going to find the rest here? What else do we know? Okay, so look at this one. This and this are tangents to the same circle from the same point. So that's 7. Okay? Next, this and this. All right, so look at the two red ones. KM and KN are tangents to the same circle from the same point. The green one, JM and JO, are tangents from the same point to the same circle, so they're each 12. When I do that, then I have one side is 19 plus 14 plus 19, and all that together is 52.
Wait, so the whole line is not the same tangent? Just that little part?
Right, it's just the part from the point to the first time it touches the circle. All right, so this homework is due Friday or tomorrow?
You don't have tomorrow.
Thursday. Oh, yeah.